Hello everyone, and welcome to today's virtual webinar about perspectives on artificial intelligence and machine learning in chemistry. So my name is Fiona Short and I'm the Senior Director for Product Management and Strategic Partnerships for Science of Synthesis. So we have a very exciting topic today that has gained real momentum in recent years. So we're really looking forward to hearing the different perspectives about AI and ML in chemistry. The Science of Synthesis team is particularly interested in this topic. We had a recent collaboration with IBM where we used our reaction data from this product to help retrain retrosynthesis and forward prediction models. And so we're very interested in any developments in this field. And of course, anyone involved in discovery chemistry or process or medicinal chemistry is also interested in this because of the potential cost and time savings for drug discovery. So there's a little bit of housekeeping that we have to do initially. This web seminar is being recorded. A link to the recording will be sent to all registrants shortly after the seminar via email. The link will expire after 4 weeks. And the audience will be kept on mute during the seminar. And please use the Q&A window to ask questions. As many questions as possible will be answered live after each scientific talk. Please tweet at Thieme Chemistry and hashtag Science of Synthesis. It would be great if you have some highlights to share them with the community for us. And if you're interested in accessing quality chemistry reaction data from Science of Synthesis, then please use this email, chemistry-tdm@thieme.de, and you'll be hearing more about this during the course of the afternoon. So some of you may not be familiar with Thieme and what we do in terms of chemistry. We specialize in organic synthesis. Some of you may have heard of our journal Synthesis and Synlet. We also have a highlights in organic synthesis journal called SynFacts, and we do have some open access journals, SynOpen and Organic Materials. We also have some databases, for example, Pharmaceutical Substances, which has over 2,500 active pharmaceutical ingredients. And we also have Science of Synthesis, which is an online reference work of organic synthesis reviews on synthetic methodology. And you'll be hearing more about our products during the course of the webinar. Just keep an eye on the links in the chat as we go along. So this WebCheminar is one of a series of WebCheminars that we're holding throughout 2023. And the next one that we will have will be on modern nickel catalyzed reactions, and it will be on Thursday, the 23rd of March, 2023. It will be chaired by Professor Ruben Martin, and there will be talks from Cristina Nevado, who is a member of the editorial board of Science of Synthesis, as well as Xiaolin Zhu and Mark Stradiotto. So put that one in your calendars right now. So coming back to today's webinar, we will have 3 talks this afternoon, each 20 minutes long, and after each talk there will be a 10-minute question and answer session. After Alain's talk, we will be having a 10-minute presentation by Dr. Sasha Hausberg from Thieme about the Science of Synthesis dataset and our collaboration with IBM to retrain their retrosynthesis and forward prediction models. So Dr. Ye Li is also a member of the Technical Advisory Board for Science of Synthesis, and Dr. Alain Vaucher is a member of the Early Career Board for Science of Synthesis. So we're very much looking forward to hearing from all of the talks and also from Dr. Marco Stenta at Syngenta this afternoon. So without further ado, I would like to introduce you to our webinar chair, Dr. Guido Koch, who is a member of the Science of Synthesis editorial board. Guido is a board member of Simple Chem and co-founder and CEO of Amphilix. From 2018 to 2020, Guido was the COO of Topidor Pharma and before a director in global discovery chemistry at Novartis. During his career in drug discovery and development, Guido has led projects in different phases from target identification to early clinical stage, including multiple kinase inhibitors. Highlights from over 20 years of experience in pharmaceutical industry include significant contributions to 1 marketed product and 8 clinical candidates. Guido has built a strong network with academia and the CRO community, which allows him to support research programs by external knowledge, new technology and resources. His research has culminated in over 45 scientific publications and 10 patent applications. Guido was educated at the ETH Zurich, and he received his diploma in chemistry and biochemistry in 1991, followed by a PhD from the University of Basel, and after a postdoc at Caltech, he joined Novartis in 1997. So over to you, Guido.
Thank you very much, Fiona, for this kind introduction, and it's really a big honor for me to chair that webinar on this topic. And this, as you just said, we're focusing today on a very actual topic, which is machine learning and AI in chemistry. It is really today in everybody's mind that this topic can transform the way how we think about chemistry and data science, and AI, I'm convinced, will become an integral part of chemistry. And so basically scientists today have recognized the power of the digital technology to transform the way how we think and practice chemistry. We have many tools available, and we are now in the process of implementing them. And we are all looking forward now to hear today from the speakers we have in our panel, how they think about the implementation and where we are with the current state of technology. What we really recognize that it is very important to build on high quality data, and this foundation is a kind of, it's really very important for generating the most let's say reliable and predictive models. And this also brings me to my role as a member of the editorial board at Science of Synthesis, which is the organizer of this webinar. Over the last decades, everybody has really realized that Thieme Chemistry and the Science of Synthesis team has put a lot of effort into generate a very rich source of validated reaction data, and we all believe that this might be a strong basis for future foundations of machine learning algorithms in chemistry. We all know that these algorithms may have an impact in how we apply chemistry in different fields, drug discovery, material science, agricultural science, etc., etc. And I'm really looking forward to learn more about all of these topics. We have representatives from different spaces in this webinar today, and so I don't want to spend too much time and just start introducing our first speaker, who is Alain. Alain is a librarian at the Chemistry Institute of MIT in the US. She is also a chair of the Division of Chemical Information of the American Chemical Society. And to come there, Alain has graduated from the University of Iowa, and she started her career actually initially as a librarian at the University of Michigan. Ye is also on the advisory board of several publishers in chemistry, including Science of Synthesis, the Handbook of Chemistry and Physics, and multiple other ACS publications. So yeah, I'm really looking forward to your talk, which is entitled Computational Access and Reuse of Curated Data in Chemistry. The floor is yours.
Thank you very much. Thanks for the introduction, Dr. Koch. Hello, everyone. It's my pleasure to be a part of this panel. My fellow panelists will highlight their cutting-edge accomplishments using machine learning and AI in chemistry. As an information professional myself, I'll start our discussion on a more foundational topic, the availability of experimental data sets for computational access and reuse. I'll also explore how different stakeholders could work together to make the data more findable, accessible, interoperable, and reusable. And before I move further along, and I just want to mention that the opinions I expressed today are only my own and are not necessarily those of my employer. And so back to the computational access and reuse. When we think of research publications and data, we use them by essentially reading them, digesting them, and processing them in our brain to learn something new. Even if we find them and read them from computer or any other digital devices, it's still our brain processing the information mainly. But in the recent decade, with the fast rising computing power, we started to have computer to process the data and texts first, and to review the pattern and insights before we absorb them in our brain. We even started to use machine to help make decisions in our research work. And we talk to ChatGPT like it's another human being at this time. And this trend is really reflected in chemistry as the fast growth of research publications on computational studies in the recent decades, really, from text and data mining to machine learning, AI, chemoinformatics, chemometrics, and all these different computational methods. Computational subdisciplines. And this fast growth is also for all subdisciplines of chemistry on different subject focus, and in the formats of both primary research articles and patents. All these progresses are built upon one foundation, the large amount of experimental data that are findable, accessible, interoperable, and reusable. So machine learning and AI can really leverage the power embedded in these fair experimental data set and turn them into insights in organic synthesis route selection, condition optimization, or optimized virtual screening of drug molecules, and property prediction in materials design. And more importantly, these models built can really direct the robotic platforms to automate the whole research process from experimental design to quality control. And none of this could really happen without the underlying experimental data sets for scientists to apply those machine learning or AI algorithms to. In chemistry, it's fairly unique that we can organize all these data around the main entity, that's our chemical substances, compounds, and materials. Their structure, identifiers, different types of properties, spectra, reactions, and even the economic data around them can be used for computational study. So where do we find this data? And fortunately and unfortunately, at the same time, they are mostly scattered in the research publications where experimentalists report their findings as individual projects and as unstructured data. Most of them are kind of locked into either print version of this publication or PDFs that we are reading them from a digital device. And to really form a data set that are machine actionable, these data needs to be digitized, indexed, sometimes validated and evaluated, and then aggregated and curated into a large set of structured data with sufficient metadata included. The better route to gather this data is really for the researchers to prepare and share the dataset in open format via the repository directly. But so far, We only made that happen systematically for crystallographic data because we started that effort in 1950s thanks to Dr. Olga Koch, founder of the Cambridge Structural Database. For those of you who know her, she just recently passed away, and we already miss her passion and leadership in the field. Before more researchers and more subdomain can really be enabled to share their data directly using the second route, we still are relying on the first route here to get the large set of curated experimental data for machine learning and AI study. And that's actually for nothing new for chemists. We actually started indexing and curating research data a long time ago. Handbooks such as the Gimlin-Belstein, indexing inorganic and organic compounds and their properties and reactions started really in the early 1800s. In early 1900s, we have chemical abstracts expanding the scope of indexing internationally, and the Hobsbawm Handbook to review and evaluate synthetic and analytical methods. All of these earlier efforts have now been turned into databases that we are familiar with, like Reactivity, SciFinder, and Science of Synthesis from Thieme. And here, I am listing a few more examples with data curated or compiled as large sets. I'm by no means trying to give a comprehensive list of data sources. I just want to highlight some examples here. As other research publications, many of these data sources are designed for humans to read and digest. Retrieving this data set in bulk is often not very straightforward, and there are challenges in terms of technological and economical, and sometimes can be legal and policy barriers. We do have some exceptions here. Those are a few government-sponsored data repositories, but for the rest of these sources, we need to be looking closer to really work together to overcome some of these barriers that can be for computational access and reuse. And looking closer at these data sources, we can see a variety of different organizations who provide them. Most of the organizations share the same mission of advancing science, but they also have their own priorities in terms of development and sustainability. Sometimes the moral justification of open science only may not be sufficient to eliminate some of these barriers for access. All the stakeholders in this ecosystem will need incentives and motivation to move towards the shared goal of advancing science, and also answer the question of how to balance the sustainability of the system and the fairness of the data. Answering that how to balance question, it will again need all stakeholders to work creatively together. I'll not attempt to do that by myself today. Instead, I'll provide some questions that we can explore together and suggest this little fairness assessment tool to help guide that exploration. And first, let's look at the some of the technological challenges. We really want to ask in the existing data sources what formats, what metadata and provenance are available. How will they be delivered and stored, and what are the limitations of that for computational use? And how much additional effort is needed for the providers to improve the data set and improve the mechanism to deliver them? And remember, because most of these data sources were prepared for human consumption directly and may not have considered the machine learning needs comprehensively before. for example, to make the data sets more findable, we would need to potentially add additional identifiers like inchi key and smiles at the item level. And all these metadata may need to be registered with some discovery services or the identifier registry to enhance the findability. And for researchers to access the data in bulk, or would an API service needs to be provided? Is it practical for the researchers to interact with data through a sort of black box platform without downloading them and closely examining them? And some of these access mechanisms are a little low barrier, but can be labor intensive. But not every data providers would have the options to develop an in-house API service. And so one more layer of technological challenge is about the interoperability of the data sets. Again, from the human readable perspective, the standardization of the file formats and the metadata standard may not be that important, but for machine to use, it's very important a standard for data formats and metadata could be adopted if it's with reasonable effort. And one more layer of that challenge is in many cases for chemistry, there are no broadly adopted standards for a certain type of data. And talking about metadata, there's also the depth of the metadata too to consider. Again, for the data out there to be consumed by a human being, we may not even have all the details extracted from the primary literature, and some of them may not have the detailed contextual metadata presented in the primary literature to begin with. For example, this schema here for the open reaction database highlighted several different metadata fields that's important for the machine learning and AI study to develop automated synthesis process. And some of these metadata can be like the stirring bar rotating rate and spectra used to calculate yields. And again, these may not have been indexed as a part of chemical reaction data when they were indexed for human consumption, because human can go back to that source to check out those parameters one by one. But these can be critical for machine learning and AI study to really develop that accurate prediction of procedural parameters, how possible it is to enrich the metadata of existing curated set for this purpose. And now let's take a look at the challenges from the legal and policy perspective. Many of these data sets started as publications. Does the copyright protection apply to the numerical data presented in those sources? And how about those ones have been validated and evaluated by the curators? And what about the arrangements of the data sets and even more complicated, that's even more complicated for the figures and the supplementary information? On the other hand, there is also the contractual limitations. Many of these sources have existing contract with academic institutions and corporations. Are these contracts enabling or limiting the computational reuse? And how about the redistribution and application of the generated data models? Reaching an agreement on these questions will really clarify the reusability status of the data sources. These license terms are also closely related to the economic challenges we have. We really wanted to ask that, like, for all the curation effort, who will pay for them, and how to assess the actual value of the curation. How should the resulting intellectual property and commercial interests be distributed so that all stakeholders, including the researchers and data providers, can stay incentivized and their organizations and team can stay sustainable. We really need to be very creative with answering those questions. For example, the return of investment for the cost of making the datasets fairer may not be monetary, but can be partnership in research or helping promoting broader use of the datasets. When redistribution of the whole datasets openly is less desirable, then could it be possible to allow a sample portion to be shared as a benchmark for benchmarking purpose? With all these questions in mind, we have seen a little bit about the challenges in terms of having a fairer data sets for machine learning and AI use. Now, I do want to highlight a few collaborations that's already happening at MIT and for really launching more curated data sets for machine learning and AI studies, and also to facilitate data sharing among experimentalists. These are the open reaction databases for organic reactions, Crypt for polymer science data and workflow, and last one is my what I feel very proud of is the IUPAC PKA dataset. All three of them are really resulted from collaborations among academic institutions, professional organizations, industry, and also government agencies. I look forward to seeing more of such collaborations happening, and really hope that librarians like myself could become more of the facilitator for such collaboration. And with that, I will stop my presentation and look for your questions. Thank you very much for your attention.
Thank you very much for this really nice presentation. Maybe I can start with a question from my end. You mentioned the PDB as an interesting way how you can share data in a machine readable format. How do you see the way forward that also other data can be shared in a similar format? So I guess this is also a kind of an important question. How do we motivate researchers to publish data in a different way or in a different format?
Yes, so thank you, Dr. Koch, for the question. One of the major barrier for experimentalists, bench chemists, to share their data in a fairer format, like what happened for PDB and CSD, the Cambridge Structural Database, is that there is no standard of sharing those data available, or well, there may be some available, but not very well adopted yet. And those standards are not really, even if they exist, are not integrated in the workflow of a bench chemist. So those are things that, from infrastructure perspective, that we can improve, and that will definitely facilitate easier data sharing from individual research labs. And along with that, when the infrastructures are in development, we also have the challenge of cultivating good practices. So data comes from our research process, and that process, if we only look at the data sharing at the end of that process, it will take much more effort to package the data and to prepare the data in a way that's shareable, and for others to be able to use them. So that process has to start from the very beginning of the research process, and the more efficient management, organizing, documenting of the data while people are doing the research is essential. There are tools and guides out there to help researchers in different disciplines to get started with that. But for individual research groups to make that happen, we really have to be very determined to do so. And honestly, all the research groups will need incentives and also facilitations, help and support from institutions, from their librarians to make that process happen. We may notice that many of those open science oriented policy requirements from different funding agencies are sort of tightening up a little bit in this couple of years and the next few years, and that will become one of the motivations for the researchers to do more of this sharing. But eventually, in practice, we have to, as a whole ecosystem, stakeholders of the whole ecosystem will have to support them better and enable them to be able to do that, to prepare the data from the very first step of the research process.
Thank you very much. So I have one question which actually is a nice follow-up question to this one from the audience. Can AI ML convert unstructured text to structured text and solve that problem?
Yes, there are I did not mention it in my presentation today, but there are many algorithms and methods have been developed to do that kind of extraction. And in fact, many of the existing smaller curated data sets are yielded from those automated process. However, because if we want to get to a large amount of curated data sets, and if we wanted to improve the quality and make it fairer, I guess those algorithms can only be a starting point at this moment. Yeah, so I don't have a crystal ball to predict like how soon algorithm can really become smart enough to just extract those data in a fairer way. But for now, I guess it's a nice complementary part of the existing data sources we have been curating for a long time. And besides those extraction methods, there are also alternative ways of amend experimental data during the process. There are many methods out there too, but eventually to allow the AI in chemistry to get as good as ChatGPT get in with language modeling, we will have to have enough fair experimental data to start with. So yeah.
Thank you very much. I think we can have one more question, and I think there is one a little bit also looking into the future. Can you tell us a little more about next steps of the big data technology to the industry to apply in the R&D process, and how it can become a reality with partnerships with academia?
Yeah, so well, that is a very big question. I hope after all of our presenters' presentation, we can have a broader discussion about this. From my personal perspective, I guess that partnership needs to start with a shared goal in terms of advancing science and advancing technology. And if you find a topic that would be interesting for academic research to build that a researcher to build that foundation, then I guess some connections can be made to first of all get access to the relevant data sets from a data provider, and then all the stakeholders involved sit down and talk about how what is the eventual model that you are looking into, and then decide how much of value of each stakeholder is adding to that process, and decide what's the best way of forming that partnership together. And I don't have a particular product or name of a model that or a methodology that I would say would be generally applicable for all types of industry in chemistry. But essentially, these are, even if a capable model is out there, it's still a part of a toolbox. So eventually, it's up to the industry or the research groups to decide where they want to lead their research and lead their product to go. And that's probably from that you can make a decision on what types of computational methods and model that can be the best to develop. Thanks.
Thank you very much, Dr. Lee, for this really interesting talk and for the answers to the questions. I think with this we can move on to the next speaker, who I would really like to introduce now. It's Alain Vaucher, and Alain is a research scientist at IBM. At IBM Research Labs in Zurich, more particularly, and he is focusing on the application of AI in chemistry. Alain comes with a PhD from ETH Zurich, where he worked in the group of Professor Markus Reyer in the Laboratory of Physical Chemistry on interactive approaches for quantum chemistry. Alain is also a Science of Synthesis Early Career Advisory Board member with Thieme, and I'm looking forward to your talk today, Alain, boosting the adoption of AI models for chemical reactivity. The floor is yours.
Thank you very much, Dr. Koch. It's a pleasure for me to be here today, and good morning, good afternoon, good evening to everyone. So, a few of you may be wondering, what has AI to do with chemical reactivity and what can we do there? And starting from the concept of a reaction as we know it, typically a reaction as depicted here, there are different questions that we can answer with AI. One of them could be, what is the product of a reaction if I know the precursors? Or if I have a product that I want to make, how can I make it? Or one could ask, what is the yield of this reaction? Or what are related reactions to the one I have here? Or under what experimental conditions is this reaction likely to work? And so on and so on. Those are just a few examples. And before going into the core of the talk, I would like to give you an idea of such AI models can look like. And the 3 slides after this one will be the most technical ones in the talk. And if you don't understand them, I'm pretty sure that you will be able to follow anyway the rest of the presentation. So one way to formulate AI models for chemical reaction is to handle chemistry as a language, where we basically consider atoms to be letters and molecule words and so on and so on. And In this context, there's a very interesting notation that has been established for already quite a few years, which is the SMILES notation. And this allows us to formulate a sequence of atoms in text form. And the beauty of it is that this allows us to borrow AI methods that were developed from for human languages. And they're typically, it's the same as ChatGPT or other algorithms. Now, I will be giving two examples of how this looks like in practice. The first one is the reaction outcome prediction, where we have a set of precursors and we want to know the product. So what we do in this case is that we convert it to this textual representation and obtain what I sometimes call a sentence of atoms. And then it is this sentence of atoms that we can translate from the language of chemical precursors to the language of chemical products, so to say, similar to a translation between French and English, for instance. And when we have this text representation of the product, we can get back the structure. Now, for the second example, which is the opposite task, so the retrosynthetic task, we do the same, just in a different order. We do a translation from the language of chemical products to the language of chemical precursors. Now, a lot of the questions that we ask in the context of AI and chemistry can be answered in a similar way. And typically, to be successful, we then simply need to collect a data set of maybe a few hundreds of thousands of reactions or a few million reactions, show it to the model, learn based on it, and then we can make predictions for new reactions or new compounds. Now, coming back to the title of the talk, boosting the adoption of these models. I think to do that, there are a few challenges that need to be addressed. We need to think about making the models easily accessible, making sure that we answer the right question, and then we also need to make sure that the models are quite accurate, that they are applicable to the fields of chemistry that interest us, and so on. And there are a few aspects of data coming. And it is these questions that I would like to focus on during the next 20 minutes. So I will start by the question of answering the right questions. And here I would like to take the example of retrosynthesis that I was introducing before. So in the context of retrosynthesis, there have been loads of new AI models to take a compound that one would like to synthesize and predict the precursors likely to work. And this is a table from a review that we published last year. This is only a selection of models. And since then, there have been many models, and this is just a selection also from the last year. And one big question when we have so many models to choose from, so to say, is how do we assess them? So the question of metrics. And there, if one looks into the papers, the common metric is to look at the top N accuracy. And this means we ask the model to make N predictions of precursors, and then we look whether the precursors that we had in the data have been predicted by the model. And by looking at all those papers, they all mention this top 1 or top K or top N accuracy. But at the same time, this metric does not paint a complete picture, to quote one of the papers. And if a new model increases a few % of this metric, it doesn't necessarily mean that this model is better. So in summary, this metric is not fully satisfactory, and it's a necessary evil, and even in our group we have been using it. And when we look at not only one single step of retrosynthesis, but at the full retrosynthetic tree, we have the same problem. And there are different metrics like the top N accuracy or Turing test, percentage of solved molecules, and so on. Now, given this situation, I think it's important to take one step back and think about what the chemists actually need, what the the people that will be using those algorithms. And in this regard, I would like to share a few of our observations with the retrosynthesis models on the IBM RxN platform, which is a freely accessible platform where we are putting our AI models for use. And so let's take the compound here, and I have a small video of trying to get a retrosynthetic analysis for that compound. So we can enter this compound, and what you see now is what we call the automatic mode. So we enter this target compound, and then the algorithms, after a couple of minutes, they come up with a few suggestions for the full retrosynthetic tree that one can choose from. And you see here, some of those have multiple steps, some of them have only one step, and so on. And this is really a fully automated mode where the chemist is blind, so to say. Now, on that platform, we also have a second mode that we call the interactive mode. And in this mode, we do one step at a time, and at every step, we ask the chemist, or like we let the chemist choose among the different suggestions, and then once they have chosen the steps that they think will be most likely, they can go to the next step. And so what I want to say with this is that we observed that chemists, they appreciate the diversity of predictions, and they like this interactive mode because they are also able to control what is happening in the predictions. So based on this observation, we started 2 projects around retrosynthesis. One centered on the diversity of the predictions, and one more on the interactivity, where the idea is to combine AI and human strength. And I will take a few minutes to talk about both of those. So first, for diversity, here I'm showing again the slide from before where we have the model. And what I want to add here is that this here is one set of precursors. We can ask the model to make several predictions in a similar way as one could expect a sentence in French to have multiple possible translations in English. Now, if we do that without special attention, what we will see is that the suggestions, they are not necessarily very diverse and may change only in one of the solvents that is predicted, or bases, or reagents, and so on, but there is no real diversity here. And so this is the problem that we wanted to tackle. So what we see is that by default, if we have a space of chemical reactions, only 1 or 2 areas, or the predictions are made only for 1 or 2 areas. And ideally, we would want predictions to be made for all areas, or for many different areas, to have many different reactions suggested. And this is what Alessandra, a PhD student in our team, did with the help of what we call the class prompts, which basically, when using the model, means that we explicitly ask the model to make predictions from all of those areas of chemical space. And in practice, we see that this works quite well, with here at the top the baseline, so the default model that basically predicts the same kind of reaction, which is here saponification. Now, when activating this special scheme, we get directly much more diverse reactions. And this, in our observations, makes it much nicer for the chemists who use these models. Now, after having talked about the diversity, let me go to the interactivity. So I mentioned this interactive mode that the chemists tend to like, and we asked ourselves, can we be even more interactive? Can we give even more control to the chemists when they use these AI models? And there, the idea was to ask, can we let them choose where to do a disconnection, where to break the compound? So typically, if we have such a compound, maybe they want to have a retrosynthetic route that changes something at the chlorine atom or at this arylic bond or at the amide group, and so on and so on. This is what led to what we call the disconnection-aware retrosynthesis, where we simply give, or we ask the chemists to specify which atoms they would like to see undergo a change in the retrosynthetic analysis, and then we ask the model to make predictions accordingly. Now, I will show a few examples of what this looks like with the target molecule in the middle and the prediction on the right-hand side. And on the left-hand side, you have the precursors from the data set. And so here we see, for instance, one where the user tags the oxygen atom here, and what is proposed is a demethylation reaction. In another case, we could have something where we want a change to happen at the carbonyl atom, carbonyl group, or where we want cyclopropanation, or maybe multiple changes at the same time, creating cycles, and so on and so on. And it was a very nice project with the model that ended up working quite well. Not perfectly yet, but this has been received quite well by people who tried it out. Now, after that, with the idea that, with the starting point that we thought that the chemists may have a good idea of where to break the compound for increasing the success probability. We then asked, actually, could the AI also take over that task, or do the same thing by learning where these connections are most likely to be successful? And for the sake of time, I'm not going to go in the details, but we did that, and we saw that it actually worked quite well. Meaning here, typically, if we show this compound, that it would suggest different bonds where this can be broken, and when we have the bonds, we can feed it into the previous algorithm to get a set of very diverse reactions, and this then feeds back into the diversity aspect that I was mentioning before, which was a nice observation. So this finalizes what I wanted to say about answering the right questions. Now, in the next part of the talk, I would like to talk about data representation and data uniformity. And why this is important is that this has a big effect on the accuracy and the applicability of AI models. What happens in the field is that a lot of models are based on the text representations that I mentioned before, such as smiles, or there's another one called selfies. And those are really very powerful, especially for organic chemistry. However, if we want to go to non-organic compounds, there are a few challenges arising. And here, these challenges are actually the same if we look at models not based on text, but on graphs and so on. And typically, we have questions on how to represent salts or complexes or special bonding situations. And often in those cases, there's no easy way to represent it. Or I could also say there are too many possible ways of how to represent those. And in the next few slides, I would like to show a few examples where I show some examples that were extracted from patent data, actually. And I forgot to say, as a consequence, a lot of data sets, especially if we look at the patent data sets, they are quite inhomogeneous. Now, the examples. The simple one would be sodium chloride, where you have already the question, how do I represent it? Do I represent it as having a positive ion and a negative ion, or do I consider two atoms that are uncharged, or do I consider two atoms that have a bond between them? From there, it increases in difficulty. If you look at lithium aluminum hydride, it can be basically all the different cases that you see on this page, sometimes with covalent bonds, sometimes with ions, sometimes where the hydride ions are are split. You also have trimers or dimers, some mistakes sometimes. It is a bit messy. Then if we go one step further, palladium acetate, you have either the fully split representation with the carboxylic acids, or again, some covalent bonds, sometimes where one is missing, dimer, and so on. And then complexes, there you start to see sometimes also more mistakes in how this was extracted from the patents, or a lot of diversity in bonding as well. And I have here also the Grubbs catalyst, and it is not harmonized at all. So in the context of AI, there are two aspects in which having conventions or having a more harmonized representation may be useful. First, for correcting errors that may be present in a data set. And second, for uniformizing the choices, like conventions, typically to say, okay, the salts, let's all represent them with covalent bonds when possible, or so on. And there we had a project about doing this in a data-driven standardization formalism. And here, just an example. So we did that with a model similar to the ones I presented at the beginning. And we have annotated a new data set of metal organic compounds, and we obtained roughly 75% accuracy on that. And maybe what was interesting also on that model is that we then took it and applied it to the task of taking a molecule and from it determining what the preferred tautomer would be based on experimental data, and this was also quite interesting. Okay, now let me go to the next one after having talked about the representation uniformity, which is data completeness. And in this context, I mean mainly reaction completeness. And this is relevant because, especially in AI, a lot of machine learning models expect reactions to be complete in terms of the compounds or the chemicals that are in there when you think about predicting a reaction class or yield or the experimental conditions. Now, the problem is that often algorithms or people will show reactions that are not really complete, but typically here for a chemist, it will be clear what it is about, but the models may struggle with it. So we basically wanted to create an autocomplete model for reactions, basically, where we can show incomplete reactions and ask the model to complete it to find a complete reaction that can then be used either by downstream AI models or by chemists who would like to know about the reagents or solvents for the reactions. And this model also applies then to the reaction outcome prediction and retrosynthesis tasks. Now, because I see that I'm soon over time, I will not go into the details, but also looking at a few examples shows quite interesting behavior, and sometimes even detecting errors in the data where compounds or essential reagents were missing, or errors in the extraction of text, and so on. And we also have an extension of that model where we can explicitly train the model to predict the solvent or predict the catalyst and so on. And this is still in preparation. Okay, now I will say very short on the last point, which is about the accessibility of the AI models. And the reason I'm mentioning it is that there are applications of AI to chemistry coming out every week. And when we think about accessibility, quite often the models are not available or have restricted availability. Quite often also it is open source, but then it's quite hard to get the code to work, or it's limited to the people with coding skills, and sometimes there are web services. Why I'm saying this is that the consequence of that is that the use by the actual target audience is quite limited, and I'm thinking especially about bench chemists who could have most usefulness for that. And there, what I wanted to mention is that because of that, we thought quite early on that it was important to have also a user interface for that, and that's the one that I included in the video before. But then this also goes to the side of having possibly programmatic access to the models to make them more easily accessible in other workflows or to integrate it elsewhere. And about this last point of accessibility, I see a lot of connections also to what Dr. Lee was talking about before, where for her it was more on the data aspect, and here I think also the accessibility of the models is quite important. And I think I will skip the next part to come to the conclusion. So the main point is that I think we need to empower bench chemists even more if we want AI to be successful in the field of chemistry. And there, it's about models being easy to use and hopefully soon also easy to retrain, that even someone who has no experience in AI could easily retrain a model. And for the future, a few things to think about are the representations, especially when going beyond organic chemistry. Also, data availability, completeness, and here there are a few nice developments that were also mentioned earlier. And with this, I would like to thank all my colleagues and also all of you for your attention.
Congratulations, Alain, to this nice talk and to the progress in RoboRxN. I have a couple of questions from the audience, which I would like to ask you here. So when you translate the reaction into the language of AI, do you see some challenges as the translation does not consider information on reagents and reaction conditions?
That's a very good question. And let me go maybe for illustration to one of the very early slides. Okay, this one. So a lot of the models that I mentioned here, and especially the ones that we have been working on in the team, we try to capture as much as possible in terms of reagents. So we not only include the reactants, so to say, but also the reagents or agents or solvents, catalysts, and so on, because we do believe that this is really part of the reaction. Now, something that we are not considering in this family of models, especially when we have this notation here, are conditions like the temperature or reaction time and so on. But extensions for doing it, and other groups have been extending the models to also include that kind of information. And this can be very relevant, especially if you think about predicting the yield of a reaction, that maybe at one temperature the yield will be very low, but at another temperature it can be quite high. So yes, this is a good question.
Thank you. And so one other question was about does retrosynthetic analysis from your tool also allow to predict multi-component reactions or domino reactions? Or does it also predict multi-component reactions and domino reaction, or does it only do retrosynthetic analysis of two-component reactions?
Yeah. So okay, let me answer the second part first. So typically cascading reactions or so, this will depend on how the data is being represented. And if in the data set the people had each step or each sub-step as a separate reaction, then this is also what the model will learn. Now, typically this is not the case, and typically, let's say, there are some reactions where several things happen at the same time. If you think about a deprotection reaction where many groups are being deprotected at the same time or also protected at the same time, in this case, the models, because the models are able to catch this, because in the end, the only thing that they see is this text here. There's no one saying this is the one of the main reactants and it must be part of the product. This is solely based on data. And so I think this in turn would answer the first part of the question, which was about multi-component reactions. For the algorithm, it doesn't matter at all if you have one main reactant that is changed only slightly, or if you have a multi-component reaction that actually combines 3 separate reactants into one big molecule or so. Those are things that the models are able to catch. And I really hope I understood the question in the right way.
Thank you. Maybe one last question. Is it also possible to detect where there could be problems, or where there could be something going wrong in a particular reaction by AI?
So is it possible to do what when something is going wrong?
To predict what some kind of problems or problematic reactions, or let's say where something can go wrong in a reaction. If you enter a reaction if you give us a reaction to the system, can it tell you what can go wrong?
So here again, let me take this slide. So partly, and I think here there will be, it is also part of asking the right questions. And I think that in this case, there can be new research that will target explicitly such things. Now, what is the case for us, especially, is that typically when doing a retrosynthetic prediction, starting from this one, making the following prediction, we will not stop here. We will do one more step, which is to take the reaction as a whole and ask the model, how confident are you about this reaction? And let me try to also show one part of the here of the video. When we see the several predictions, we show here in the middle also this confidence at which the model is thinks this is likely to happen, and we indicate also that here typically it has medium confidence, and that's one way in which the algorithm could say, I'm not so sure about that.
Thank you very much. I think with this we can move on to the next presentation, which is from my colleague Sascha Hausberg from Thieme, giving a brief presentation on the IBM collaboration.
Yeah, thank you. Guido, can you see my slides?
Yes, that's good.
Okay, wonderful. Good. Thank you, Guido. Thank you to all the speakers, and thank you all for joining our WebCheminar today. I will give you a very brief introduction to science of synthesis and our efforts around the data of science of synthesis. So we heard already a bit about science of synthesis from my colleague Fiona. Science of synthesis is a major reference work, and yeah, it's evaluated methods reviewed by world-renowned experts. It's all author-written, so it's secondary literature. In total, there are more than 2,000 reviews, and it's a highly structured content, and in it, it's the largest full-text resource for evaluated methods in synthetic organic chemistry. So it gives you the full overview of everything that is organic synthesis. But it's not only the full text and the methods, but over the course of the last 20 years, the according reaction and structure data has also been curated most of the time in a manual way. And by that, we have created a set of over 460,000 reactions. Around 10 to 15,000 reactions are added on an annual basis. And on top of that, we also have more than 50,000 or 55,000 experimental procedures, and of course the underlying molecules for that. So the whole data set is available in different formats. For the text, we have, of course, the XML and PDFs. We have schemes in Chemdor format. And for the structures, we have SD files and RD files and SMILES for the reactions. So over the last 1.5 to 2 years, we took a more detailed look at the data set. For example, we performed a name reaction analysis and classified this content. About 1/3 of the reactions were classified using one of the popular name reaction classification tools on the market. 2/3 remain unclassified so far, which is not a bad thing, because that shows how diverse the data we have in the science of synthesis data set actually is. But of course, we're trying to also find out more about this part of the reaction data set to show the diversity also in terms of facts that we can share. And Guido mentioned this already, and we have worked over the last 1.5 years together with IBM in the RxN project, which Alain also talked about a bit. And we started this with a number of questions, namely, can the combination of the powerful AI coming from the IBM side and the high quality data coming from the Thieme side, can this lead to better predictions for chemists? And can we, with this collaboration, can we improve the tool? Can we lead to a better adoption of the tool by chemists and make it more useful for their daily work? And in the course of the collaboration, one of the goals from Thieme side was also to find out how valuable is our data that we built over the last 20 years and curated. And the qualitative feedback was, yes, this absolutely works and leads to better models and to better insights using RxN, using the RxN tool. So compared to the models based on patent data only, almost always the steps reduce the complexity of the target. It led to a wider range of chemistry included in the model, in turn giving more useful results and most importantly, different types of transformations, and also led to better capturing of for example, photochemistry. We had one particular feedback from industry users saying that the Thieme models were always rated as better performing and making more intuitive sense. And that was from a evaluation where 8 to 10 industry users use the models on a daily basis. So as a result of this evaluation, what we learned at Thieme about the data we provide is we can apply the data to help AI software which is focused on optimizing chemical reactions. So our quality data can make a difference there. We can improve retrosynthesis and forward prediction algorithms with that, and help these tools to access a broader chemical space than, for example, with patent-only data. The quality of the data and the amount of work that was put into the creation of the data can be seen, because from the science of synthesis data, a large percentage can be readily accessed and readily used in these models. So about 75% was usable. If you compare that to the patent data set, we're at about 35% there, so that's a massive improvement. And since we're coming from the science of synthesis major reference work, which contains validated synthetic methods, the underlying data represents this as well. So one can be sure that these methods actually work in the lab. And of course, with the additional analysis work that we're putting into the data, we can also easily compile subsets of the whole database for specialized applications. So that collaboration for us was very useful to learn more about the data. And if this also sounds interesting for you, please get in touch with us, either with my colleague Fiona or with myself, or through the email address that was mentioned before, chemistry-tdm@thieme.de. And maybe we can help you in your project, in your AI and machine learning project as well. Thank you very much.
Thank you very much, Sasha, for this interesting introduction into the collaboration of Thieme and IBM. And I think with this, we can directly move on to the next speaker of the webinar, who is Marco Stenta. Marco is the leader of computational chemistry team at Syngenta. He supports with his team research projects in agricultural discovery activities, and this involves implementation of computational platforms that support property-driven molecular design of active ingredients, considering also synthetic accessibility. And to do that successfully, the team has created data models and ontologies for chemical and reactivity data, reactivity models, and reaction prediction tools. Marco has received his PhD in medicinal chemistry in 2008 from the University of Bologna in Italy, and he did a postdoc at EPFL. Marco, I'd like to hand over to you for your lecture about design, synthesis, test, analysis process in the digital era. I'm looking forward to your talk.
Thanks. Hi, everybody. Good morning, good evening, good afternoon. Thanks for hosting me and allowing me to share a bit of the experience that I have acquired in the past few years in developing some of the platforms that would leverage the innovation in the digital area in an industrial context. As Guido mentioned here, my journey started from molecular simulation in academia, and then when I joined Syngenta, I did the design of active ingredients, and I experienced the pain of not having the tools that are available now. And since a couple of years, I moved into the area of designing and implementing such platforms and bringing this new wave of technologies into the hands of people. I will express opinions that are mine in the next 20 minutes, but the learnings that I will share with you have been acquired with a pretty large team, and I would like to explicitly mention a few individuals that have been critical for the work that I will show to you. Guillaume and Serge for the synthesis part, Fides and Federico for the design and the new approach to design, We work with external partners for the development, EPAN, brilliant teams across all Europe, developing and deploying infrastructure. We have learned a lot working with them. Also, we work with pretty smart people behind excellent software like RDKit and Greg, NextMove and Roger, the Biosolve IT team and the Chemaxon team that allow us to do what we want to do. We also collaborate with industries like IBM. We work with academics like the MIT professors for retrosynthesis prediction and reaction modeling. And we use and leverage open innovation coming from, as an example, AstraZeneca with their products for both retrosynthesis, IA, Zyfinter, and inverse design reinvent, which will be the topic of this discussion. Before moving into the real core of the presentation, I would like to repeat the problem. And I would like to share with you the fact that although we work in agrochemistry and we design agrochemicals, the problem that we face is very similar to the one that pharma industry face. It's more or less the same thing. And whatever I will say probably applies as well for pharma. The problem here is that both industries, we want to design active ingredients with a set of properties that go from biological activity to safety. And for us in agrochemically, even more stringent are the problem of sustainability in the form of making sure that our products are not harmful for complex ecosystems, and cost, of course, because we want our products to be viable for the farmers, the people that will use it. So a lot of properties that we need to consider all together from the very stages of our projects, and that's a difficult task to balance those properties together. On the other side, since the amount of time and resource that we have is not unlimited, we need to make decisions every day for the next compound we make, but also generally which project has a higher chance of succeeding and which one is better to stop. And we need to make those decisions only when we are confident, because we don't want to lose opportunities, but on the same time, we want to stop projects that are not going anywhere and leave room for more promising projects. So properties, a lot of constraints, and we work also in the realm of molecular space. So the chemical space problem is very simple to state. There's just too many molecules out there to make. And if I got the math right here, it would be impossible to enumerate and make them all and test them all, not only physically, but even virtually. So we cannot make virtual compounds and apply to them predictive models and explore systematically the chemical space. Just it's not the time we have ahead of us is not enough. So this means that for those two problems, the fact that our desired property space is very restricted and a lot of constraints apply, and the fact that the possibilities are immense, it means that we need to be extremely smart in the way we approach the problem and we try to solve it. So the topic of our discussion here works around those two areas, and I am very glad that my fellow panelists introduced the topics already, so I can build on what they said, and you will see that what I say resonates very well with their comments. First of all, digital technologies needs to be a part of the discovery process. If you have a nice technology, which is a nice tool, and you don't embed into the very fabric of the process, this stays very likely as an expensive toy that sooner or later will start gathering dust and people will forget about it. So it will not be transformative in the way you do your research. This means that often you need to rethink the invention process. So process cannot be amended, but need to be redesigned from scratch. That's what we will see today. And also this means that there is a change management aspect. And what I will touch today is how does technology impact the work of people and even the feeling how people will reciprocate with those new technologies. Other aspect touching on the data, and here I echo the fairness, the need for fairness. So if we imagine that AI is a way of automating some decision making based on models, machine learning, then we cannot have a meaningful machine learning if we don't have plenty and excellent data. And without excellent data, anything else is just a delusion and we don't go anywhere. And we discussed about how we can do without curating the data using models to semi-curate them. That's definitely good and important retrospectively, but at some point we need to decide that, and that's what we did. We decided that it's the moment to get the data in the right shape for the future, for the application that we envision, so that we don't need to rely on very painful data curation processes. Here I introduce the concept of the DSTA. That's the process that we use to invent active ingredients, material, and it's basically a version of the scientific process. In this case, I usually depict it as a Ouroboros, this mythological snake or dragon that eats itself in a circular way, because also this process is circular and iterative. And each time we iterate through the design, which is the generation ideas, the synthesis of molecules, the testing of those molecules in our assays, and the analysis of the data, we generate information that feed the next cycle. So the smaller the number of those cycles and the quicker we get to the right property space that I introduced a moment ago, the better we are. We can get sustainable products at a fraction of the cost and everybody benefits. So this is the thing that is under our inspection, the thing that we want to improve. Of course, this is implicit. We cannot throw away this process. Again, this is based on the scientific process and it's pretty good overall. And we don't have any alternative, so we need to stick with it. Of course, we tried and we still try to improve each of the steps of this process alone. But we realize that this has not a transformative impact. This is just an incremental improvement of the process, which is likely not enough for us to meet the very strong challenges that we face in terms of inventing new compounds in this very chaotic external environment. So we need to find other ways to relink, to rewire the linkage between those steps so that we can extract better value while we inject new technologies. So let's see what we can do about that. So let's start with the design, which is the very first part of my presentation. And here I would like to refer to the brilliant work of Nobel Prize Daniel Kahneman that explained the functioning of our behaviors by creating a framework, an interpretative framework for the functioning of our mind. And here I will attempt to do something similar to describe what it is into the design box. Of course, if we say that the design is the creative endeavor of the enlightened mind based on his experience, we don't go very far and we cannot do anything to improve the mind of people. So we need to find a way to understand how the technology can impact the design. So let's try together having this conceptual framework for the design. Of course, we need to start from the analysis and rewire the link between analysis and design. In the analysis, we can imagine that something happens in the brain of a scientist that links together the structure of molecules and their properties in what we call structure-property relationship. This can be qualitative, and this happens every time we look at a table of compounds with their activities. The first step of design, proper design, is when a scientist, usually a medicinal chemist, sketch in the whiteboard of their mind a number of chemical structures based on their experience in chemistry, in synthesis, in projects. And the second step, after this generative step, is the pruning of those ideas using the SPR, this qualitative model, so that what is left are just the structures, the ideas that stand a higher chance of being successful. After synthetic accessibility assessment, we can only test what we can make. Then we move on and we pass them on the testing and we start the cycle. Of course, computer already helps and has helped us since many, many years by making a quantitative the structure property relationship. And here we can go from very simple linear models to very complex deep learning models to create relationship between structure and property that can be scaled up and filter very large amount of compounds. On the other side, people can cluster together, put their minds together, and also use algorithm and dictate the behavior of those algorithms in a very prescriptive way, so that you can generate a lot of structures and filter them. So far, so good. So what is the problem with this? Let's look at the details of what's happening here. We know that the data inform directly the selection part of the design. We have those beautiful predictive models, and if we make them right, and if they are accurate, we can scale up and we can inject information from the data through the model into the selection. But the generative part, the generation of idea, the generation of the structure is still entirely an activity dictated or just plainly done by individuals, by human, by people with their experience and their knowledge. And it's difficult to scale this part. Now, the problem is that we work in a complex environment, and the problem is intrinsically multiparametric. And we know that our brain struggles in dealing with multiparametric processes. We translate a multiparametric problem into a series of monoparametric sequential problems. And this is not good enough considering the constraint that I mentioned a moment ago. So what do we do here? So the idea was floating around since a lot of time, just we were not able to do it so far. The idea is that, so in the current status, what we call direct design, we have that the properties are a function of a structure, and we can assess whether a structure is good or bad by predicting the property, and we filter them out or we keep them in. But what if we had a tool and we give to this tool desired ranges of properties, and this tool gives us structures instead? So this is what we would call inverse design, and would solve the problem of this data leakage, because the data through an analysis process and a modeling activity would inform both the generation and the selection. But again, this was not possible to a good scale until a few years ago. And here I call 18 the year where the revolution began, because two technologies, one about design, so allowing this inverse design approach happened, was available. People like me could test it and see that they kind of work. And also the synthesis that Alain just presented a moment ago, and then I will talk in a few minutes. So we focused in trying to use and deploy into projects approaches based on inverse design. And we focused especially in the technology developed by AstraZeneca, which is called Reinvent. Open accessible, you can look at the code, you can know what's happening, you have full control. That's brilliant piece of science happening there. The way it works is, even if overall it appears like you give properties and you get molecules out, there is a virtual optimization cycle happening, and that's what I want to show here. So the tool generates molecules, and the molecules get scored with a number of models, predictive models like LOC-P or solubility or toxicity, pharmacophores or docking, if you have such information available for your project. Those scores get combined into one score through a multi-parameter scoring profile, and this is fed back into the algorithm, and the algorithm learns and gives another generation of compounds that very likely meet those multi-parameter criteria slightly better, and so on for multiple cycles until later we run out of time or patience, or the compounds that we can harvest are good enough to send to the chemist and evaluate their synthetic feasibility. So we tried this approach in projects. Almost 70% of our projects are supported by inverse design in a form of another. And that's what I want to share with you, some of the learning. Let's make a summary of what we have seen so far. So we have inverse design, this new technology that is entirely driven by algorithms, fully autonomous in the generation and selection of compounds. This works very well when you have plenty of data and when the model are very good, what I call high data regime. Machine are very good in interpolating and in finding patterns that may be invisible to the human eyes, or patterns that are multi-parametric by nature, so are difficult to extract by individuals. On the other hand, we still don't discard and throw away in the garbage bin the direct design approach, where people generate and co-select compounds together with machine, with the algorithms. Why? Because this works very well when you operate in a low data regime, when you don't have data enough to make a model, or when you are on hypothesis based, when you want to make, or you envision how to make only one compound to discard or to confirm one hypothesis. And this is where individual human mind excels. So here you see that we can envision how to split the work. And if we were able to delegate to the machine the part of the design in the high data regime, we will liberate some of our time as scientists to work on the problems that are more challenging, more difficult, that cannot be tackled by algorithms, and honestly, that are probably more fun to deal with. So this is probably something that we need to work on how to do this split between machine and individuals. There is another aspect that is hidden on the topmost corner here on the right-hand side. An algorithm can bring you where you want to go in terms of property space, but cannot tell you where you want to go. You still need to decide which are the properties you need. It's like with the self-driving car, you still need to tell it where you want to go, and then you let yourself be driven to it. So this brings to the final slide on the learnings. We discovered that the creation of meaningful multi-parameter profile is extremely challenging, and translating the qualitative project critical success factors, IP, okay, good activity, chemical scope, okay, into something that is quantitative and an algorithm can understand and use for the process that I described a moment ago, that is extremely challenging. But it's extremely healthy for the project, because they start discovering what really matters for the success of the project itself. And it's where the project teams start to having meaningful discussion, not about preferring one compound over another, but rather what is important in terms of priority of a project. When this happens and we have the models, we have the right data, multi-parameter optimization really works and brings you in the desired region of the property space very fast, very efficiently, and very effectively, I have to say. Still, in many cases, we discover, not much of a surprise, that acceptance of the suggestions from those algorithms tend to be low, and that's for their low synthetic feasibility. And we decide to tackle this radically and have a description of synthetic feasibility embedded into the generative models. So being this our vision, we started investigating how we can complement those generative models with reactivity models. And here I connect myself to the presentation of Alain a moment ago, that introduced very brilliantly the concept and the need and the potentiality of reactivity modeling. This started again not many years ago. We had already examples of retrosynthesis prediction, and we were able to perform reactivity modeling using fingerprints or other approaches very locally. For me, in my position in my company, the revolution happened because we were able finally to generate global models leveraging only on data with minimal input and efforts from experts in curating and manipulating and impacting the data. This was really transformational and has a lot of potential. Quick recap about what reactivity modeling can do: predicting products, predicting reactants, whole retrosynthesis tree, the yield, the solvent, other reagents. Also, we can have some other very nice byproducts like atom-to-atom mapping, which is extremely important byproduct of this type of modeling. And this translates into a set of requirements that we have for those platforms that provide reactivity modeling. Until a few years ago, there were only two big commercial providers, CAS and Reaxys, that provided both the data, the algorithm, the model, the graphical interface. and we use them, and we try to embed them into the workflow of our synthesis design. The landscape, fortunately, got much more complex and complicated by the rise of other people doing sciences in this field and providing alternative solution. So Alain mentioned a lot of publication in the academic world that every week publish new methods, new algorithms, new variants. And my learning here was that it's pointless to try to pick up the best. There is no such thing as the best. Each of those tools and platform and model are complementary to each other in terms of features, but also in terms of approach. So it makes sense to try as much as one can, keep more than one of them, and use their combined consensual results. Of course, the data is another aspect, and we have seen that we can have access to other data, and why not mixing and matching the models and the algorithm and the data in different ways. So this creates a combinatorial explosion that is not sustainable for a company, because that's not the work that we want to do. And when we try to expose to the bench chemist this complexity, the uptake was close to zero, because people cannot go and perform their presentation, their reaction multiple times and embed the results. So regarding the data, before starting doing anything, we wanted to make sure that the data have a value, that we can retrain those models with proprietary data, with other data sets, and those data sets have an impact. The model is steered, the quality improves, because again, we want to use those models to steer our decision making. If the model is not good, our decision making will be poor and we will not trust it anymore. So an expensive toy taking dust somewhere. We were successful together with IBM. We ran this collaboration. We discovered that the value have indeed, that the data have indeed a value. And this was the moment where we decided to have an approach where we try to tackle this problem of combinatorial explosion of possibilities, making sure that we can leverage on all the data that we can get the hands on all the platforms that we can have the hands on, and unify the access and simplify the work of the users. So what did we do? We start everything with our compass on the modeling. So we say we want to use the model at the best, we want to embed them in our workflow. So what do we do then? First of all, we have data, and models and prediction are not enough. We need explainability often of why a model predicts a certain something. So we had to put together also a reactivity analysis platform. Then we tackled the very core of our process, which is the replacement of the electronic lab notebook. We call it reaction data management, which is the tool that helps a chemist to synthesize a compound, simplifying and automating all the search, stoichiometry, similarly to an ELN, but with an extreme care on the data. We allow nothing to be either free text or to be left to the chance. What we introduce is a synthetic design part, which is the part that takes as an input reactivity models and the insights from the reactivity analysis platform. And this is where we design our routes, where we combine the results of multiple tools, we score the routes, we compare them, and we allow the user to decide which is the road to their targets that they pick. The synthesis leaves not just an exhaust at the end, which is the data, but something that is very well curated and goes into the reaction data lake alongside other sources. And from the reaction data lake to modeling and data pipeline, close the data loop and allow to retrain new models and generate new insight in the analysis platform. So this is a bit our vision. We started to implement one piece at the time. We are kind of 3/3 out of 4 in 3/4 out of 4 in this journey, and we are already reaping the benefits in terms of efficiency, in terms of effectiveness, in terms of HSC, leaving nothing to chance, having better analysis of the sustainability of our process, a better care on the HSC aspects of those processes. This is done easier and faster with this approach. So again, quoting Gibson, you read the quotes, we believe that this is possible, just we need to make it in the proper way. We need to make sure that, yeah, we are able to integrate those new technologies into the fabric of our processes. Take-home messages, very briefly, my last slide. We should not accept another idea generator, neither for design nor for synthesis. We need those models to be as accurate as possible. We don't have to compromise here because we want to base our decision on it. The human aspect here is want to remember the idea of delegating to the machine as much as possible so that we liberate intellectual time for critical, difficult tasks that machines cannot do. That's extremely important. It's very emotional sometimes. There is very strong change management aspect. Up in the food chain means that we need to stop as much as we can taking decision based on data, but using models, because the data are just too much, too chaotic, and we would be much better if we were able to take decisions on model. Decision on models means still having the data in the back. Data have a cost, model have a cost. We need to pay this cost somewhere if we want to this vision about AI to be real and not just a hype and a buzzword. The other aspect that is what Alain mentioned at the very end is about usage and usefulness. The best model, the best platform that is not used for whichever reason is useless. And we cannot afford having those expensive toys parked somewhere in a corner of our company. So our effort is the integration and an effort to generate fair data in the first place. And with this, I close and I ask your questions.
Thank you very much, Margot, for this excellent presentation and the insights into how you work on optimizing the design, synthesis, analysis, test cycles. I have a question. So you mentioned that in your reverse design approach, it's really about data. And what is the most critical data for having a successful reverse design approach?
We started with predictive models, like trying to predict the biological activity. We work mostly with phenotypic screening, but our experience is the same in other companies that do pharmaceutical active ingredient design. So we started with predictive models, but we soon realized that they were not enough because they either are not good enough to few data points, or they restrict you in a chemical space that you don't want to be. We started having real success when we introduced molecular models. Docking, when you have the luxury of having the docking, this really boosts the quality of your design tremendously. But what we think is the real success, and this is a bit anticlimactic if you want, is pharmacophore models. You can build a pharmacophoric hypothesis even with 3 compounds. And if you have a good way of representing your pharmacophore and giving it as food for this algorithm, you can leverage insight even in the absence of a lot of data. And then you start the cycle, not the virtual cycle that I am describing in this slide, but the physical cycle of making those compounds. And we had one particular project where we refined the pharmacophore into 3 different consecutive DSTA cycle, and we got into the property and chemical space much faster than we anticipated for such an early stage project. So anticlimactic answer is pharmacophore works absolutely great if you can use it.
Thanks a lot. Maybe for a final question, how would, from you, from a computational chemist's aspect, an ideal platform look like, and what does that mean for a lab chemist?
Well, what we are designing is not for computational chemists. Whatever we are designing in the platform, I hope you see my slide here, everything we do is targeted for the chemist on the bench, because the idea is not even to improve the performance of chemists that are super expert in retrosynthesis. We really want to help the people on the bench, provide them with tools that on one side allows them to outperform themselves in terms of finding new ideas at a fraction of the time. Second is allowing them and simplifying their task to generate the data. So in here I connect to what Thieme was saying. Generating data at fair level is something extremely costly in terms of time, in terms of effort. So we put a lot of effort in our RDM module to simplify the task of people in generating those data, because they don't see immediately an advantage in getting data of very high quality. For them, what matters is getting the sample out for testing. So an ideal platform needs to help the experimentalist, and an ideal platform needs to help them getting good insight, good prediction, and also allow them to generate new data and close the data loop.
Thank you very much. I think with this, I'm coming close to an end. I would say I would really like to thank everyone on the stage today. We had 4 excellent presentations giving us some more insights on how AI, machine learning, and data science can transform the way how we think about chemistry, how we perform synthesis in different let's say applications. So thanks a lot. It was fantastic to listen to you and to discuss with you. I would say I like to hand back to Fiona.
Okay, thanks very much, Guido, and thanks very much to everybody this afternoon for the wonderful talks and the really great insights. I think having Ye's talk about sourcing the data and the legal and policy challenges that we have, as well as curation considerations. Alain, you're talking about the use of data for prediction and modeling, improving the technology, and also finally accessibility for the end user was very interesting. And Marco's talk on the use of digital technologies as part of the discovery process in industry. So thank you very much to each of you for the talks today, and thank you, Guido, for moderating the entire event. Also Sasha, for my colleague, for the presentation on the reaction data. It was great that everybody joined us today, and thank you very much for listening, and have a great day everywhere. Thank you. Bye now.